Welcome to Lecture 4.3, the Fundamental Homomorphism Theorem. Before we begin, let's motivate this by using the example from the very end of the previous lecture. There, we had a homomorphism phi from the quaternion group to V4 that sent I to the vertical flip V and J to the horizontal flip H. Since I and J generate the quaternion group, it was relatively easy to determine the image of the other 6 elements, and this is what they were. Let's quotient out by the kernel of phi, which is the elements -1 and +1. The first step is to organize the Cayley diagram by the subgroup K, which is the kernel, which is generated by -1, so that's right here. The left cosets of K are near each other, so you can see them visually. They are those identical copies of K that permeate the Cayley diagram. And when we collapse those cosets into single nodes, we get a Cayley diagram right here that looks just like the Cayley diagram of the image of phi, which is V4. So the key observation here is that Q4 mod the kernel of phi is isomorphic to the image. And that leads us to the fundamental homomorphism theorem, which is one of the central results in group theory. If phi is a homomorphism from G to H, then the image of phi is isomorphic to G mod the kernel. The fundamental homomorphism theorem says that every homomorphism can be decomposed into 2 steps. Number 1, quotient out by the kernel, and then number 2, take the Cayley diagram that you get and relabel the nodes via phi. So in the previous example, we had Q4, the quaternion group, and we had a homomorphism from there to V4. And that series of 3 pictures I showed you is that instead of this direct homomorphism, we can first do the quotient process to get Q4 mod the kernel, and then we can just relabel those nodes. Now the nodes of this are cosets, but if we relabel them according to phi, then we get the Cayley diagram of the image of phi, showing that these 2 groups are isomorphic. And this last step is an isomorphism, because it's just a relabeling that preserves the structure. Let's prove the fundamental homomorphism theorem. So what we will do is we will construct an explicit mapping from G mod the kernel to the image, and we will prove that it is an isomorphism. So as before, we will let capital K denote the kernel, and recall that the quotient group G mod K is just the set of left cosets A times K. And it could be right cosets too, because this is normal. Those things are the same. So we'll stick with left cosets. So how do we define this map? We want to define a map I from G mod K to the image. So the input of this map is a coset G of K. And what element in the image do you think we want to send this to? Well, there's not many choices, right? How about that? Phi of G. That's simple. It works. Well, does it work? First, we have to show that I is well defined. And remember what this means. That means that we could have many different ways to express this left coset, and therefore we might have many different phi of G's. And it better be the case that, say, if you and I both choose a different coset representative and we apply this definition, that we better get the same result. In other words, we must show that if AK equals BK, then I applied to both of these cosets, which are the same, have to be the same. Suppose that AK equals BK. So what should we do with this? Well, you can't stop me from multiplying both sides of this equation on the left by B inverse. And that gives us this. So B inverse A times K equals K. So this left coset equals K. That can only happen if this element is in K. So B inverse A is an element of K. In other words, it's in the kernel. And by definition of the kernel, that means that phi applied to this element B inverse K has to be the identity in H. Now, what do you want to do with this? Phi of the product of two elements. Hopefully, you look at that and say, well, let's use the property of homomorphisms to break it up as phi of B inverse times phi of A. Okay? And now what? Phi of B inverse is just phi of B inverse. So that's this. Phi of B quantity inverse times phi of A. And now, what does this say? So the identity element is the inverse of this times A, and that of course means that phi of A equals phi of B. So by definition of A, I of AK, which is just phi of A, is equal to phi of B, and this of course is equal to I of BK. And that's exactly what we wanted to show. That if you and me have different choices for coset representative, if I choose AK and you choose BK, and we apply this definition of I, then we better get the same answer, and indeed we do. So our map is well defined. Next, we have to show that I is actually a homomorphism. So to remind you what I is, I've put it up here. It's defined. So we must show that I of the product of two cosets, I of AK times BK, is equal to I of AK times I of BK. So let's just use the definition and nothing else. I of AK times BK, now the definition of the product of cosets, AK times BK is just ABK, remember that? So that's I of ABK. And now, what's the definition of this? I of ABK, use our definition of I up here, and that's phi of A times B. Now, what do you want to do with this? You want to break this up into two pieces. Phi of A times phi of B, because phi is a homomorphism. And now what are these things equal to? This is I of AK and this is I of BK, just by definition. And that's what we had to show. Therefore, I is a homomorphism. Okay, so we have a well-defined homomorphism from G mod K to the image of phi. We have to show now that it's an isomorphism. So we have to show that it's onto and one-to-one. Let's do onto next. So what does this mean? Well, it means that for any element in the codomain, in this case that's the image of phi, that there is some element in the domain, which in our case is G mod K, that gets mapped to it by I. So let's pick any element in the codomain. Let's call it phi of A, and let's ask, so we're over here, what element in the domain gets mapped to phi of A via this map I? Well, hopefully you see it. It's just the left coset, AK. So by definition, I of the coset AK equals phi of A, and therefore I is surjective, or onto. And notice that we're not asking whether phi is onto. And in general, it need not be onto. There's no reason that it has to be. We're asking if the map I, which is defined in terms of phi, but it's very different from phi, whether that map is onto, and indeed it is. At this point, we know that I is a well-defined homomorphism that is onto, so the only thing that's left to show is that it's also one-to-one, because recall that we're trying to show that it's a bijection, so it's one-to-one and onto. So how do you show that a mapping is one-to-one? And there's several ways, but this is probably the most common. And here's a nice picture of it first. So let's suppose that you have two elements in your domain. In this case, those are left cosets, AK and BK. Now, a one-to-one map, the way to think about it is that it sends unique elements in the domain to unique elements in the codomain. So you never have two elements going to the same place. So you never have something like that. That is not allowed. So that means that if AK and BK get mapped to the same element, in other words, if I of AK equals I of BK, well, then these elements must have been the same to begin with. So AK and BK have to be the same. So that's what we'll show. So to start, suppose that I of AK equals I of BK. Well, then by definition, I of AK is phi of A, and I of BK is phi of B. So let's multiply both sides of this equation on the left by phi of B inverse, and then we get the identity on the right, of course. So now what do you want to do when you see this? Well, let's use the homomorphism property and write it like this. Phi of B inverse A equals the identity. So if this element, B inverse A, gets mapped to the identity, then it has to be in the kernel. So B inverse A is in the kernel K. That's just by the definition of the kernel. So now what? Well, if B inverse A is in the subgroup K, then the left coset, B inverse AK, has to be equal to K. And that's just a general fact that for any subgroup H, if a left coset AH equals H, then the representative A has to be in the subgroup itself. So now what do we do from here? Well, let's multiply on the left by B. And that tells us that AK equals BK. And that's exactly what we wanted to show. We wanted to show that if I sends AK and BK to the same element in the image, then that had to be the same coset to begin with. So AK equals BK. So therefore, I is injective. And in summary, since I is a mapping from G mod K to the image of phi, that is a well-defined homomorphism that is injective, or one-to-one, and surjective, or onto, then it is an isomorphism. Therefore, G mod K is isomorphic to the image of phi, and the fundamental homomorphism theorem is proven. The fundamental homomorphism theorem has a number of consequences and corollaries, so we'll name a few right here. Here's a simple one. If we have a homomorphism, phi, from G to H, well then we already know that the image of phi is a group, namely it's isomorphic to G mod the kernel, and it's also a subset of H, therefore it has to be a subgroup of H. Here are a few special cases of this. On one hand, if phi is an embedding from G to H, then by definition, the kernel of phi is just the identity element in G. So what does the fundamental homomorphism theorem tell us about this? Well, it says that the image of phi is isomorphic to G mod the kernel, which is just G mod the identity, which is isomorphic to G. For a visual picture of this, let's suppose that we have a homomorphism phi from V4 to, somewhere else, H. It doesn't matter. I want to draw the Cayley diagram of this, so E, V, H, and R. And if the kernel is just the identity, and then we do the quotient process, So here are the left cosets of the kernel, and if we quotient out by those, then nothing happens, and the resulting Cayley diagram is the same. So G mod the kernel is equal to G. On the other end of the spectrum, suppose we have a homomorphism that sends everything to the identity element. So this is the trivial homomorphism. Then the kernel, of course, is equal to the entire group. So what does the fundamental homomorphism theorem say? Well, it says that the image of phi, which is just the identity element, is isomorphic to G mod the kernel, or G mod G. And we know that to be true as well. So the same example that I just used before, suppose we have a homomorphism, how to say it's from V4, and the kernel is everything, then here's the kernel, and if we quotient out by that, that shrinks the entire diagram down to one node, and G mod the kernel, of course, is just the trivial group, and the resulting Cayley diagram has a single node. Now, let's use the fundamental homomorphism theorem to determine all homomorphisms phi from C4 to C3. By the fundamental homomorphism theorem, G mod the kernel is isomorphic to the image, which is a subgroup of C3. And there aren't many subgroups of C3. By Lagrange's theorem, that says the size of a subgroup divides the size of the full group, the order of the image of phi has to be 1 or 3. On the other hand, we know that the kernel of phi has to be a subgroup of C4, that is the domain. And Lagrange's theorem also says that the size of this subgroup divides the size of C4, which is 4, so the kernel of phi can only be of size 1, 2, or 4. Therefore, the size of the image has to be 1 or 3. But we know by the fundamental homomorphism theorem that that must be equal to the order of G mod the kernel. And what are the possibilities of that? Well, also by Lagrange's theorem, that's either 4 over 1, or 4 over 2, or 4 over 4, because the kernel can only have size 1, 2, or 4. So this number, whatever it's equal to, is either 1 or 3, and it's also either 4, 2, or 1. So the only possibility that satisfies both of these is 1. So this has to equal 1. Therefore, the order of the image is 1, which means that the only homomorphism from C4 to C3 is the trivial one, namely the one that sends every element to the identity, because that's the one where the image has size 1. Now, I want to talk about another very useful consequence of the fundamental homomorphism theorem, and this is a general technique of how to show that two groups are isomorphic. The standard way to show that two groups are isomorphic is to construct an explicit isomorphism between them. So this means that you have to define a mapping, you have to show that it's a homomorphism, you have to show that it's one-to-one, and you have to show that it's onto. When the domain, when this G is a quotient, then there's another method due to the fundamental homomorphism theorem. So let's suppose that we want to show that, say, G mod n is isomorphic to H. There are two approaches. The first one is what we did to prove the fundamental homomorphism theorem. We defined a map from G mod n to H, and we proved that it's well defined. We proved it was a homomorphism. We proved it was a bijection. And in theory, you could define a map the other way around. There's nothing wrong with that. And then if you did, you would not have to show that it's well-defined, because you only have to show that it's well-defined when your domain consists of cosets or of equivalence classes. Because when that's the case, then your definition very frequently, or almost always, depends on your choice of coset. Or it seems like it could depend on your choice of coset, and you have to show that that doesn't happen. In other words, if I choose a coset, say A n, and you choose a coset B n, then we have to show that we get the same answer using our definition of phi. Fortunately, the fundamental homomorphism theorem gives us another technique, which is frequently easier. So instead of defining an explicit mapping between these two groups, proving that it's a well-defined bijective homomorphism, let's define a map from G to H. So even though our domain is G mod n, group of cosets, let's just define a mapping from G to H and prove that it's a homomorphism, prove that it's onto, and if we can prove that the kernel of this map, if we can construct it in such a way that the kernel is equal to n, then by the fundamental homomorphism theorem, G mod n, the kernel, is isomorphic to the image, which is H, assuming that the map is onto. And that's what we have to prove. Now this may seem like a complicated method, but usually it's actually easier. Because showing something is well defined or showing that something is one-to-one can often be tricky. For example, each of the following are results that we will see very soon, for which method 2 works quite well. I'll actually show you this one on the next slide. So this says that the quotient of the integers and the subgroup generated by n, which are the integers that are multiples of n, is actually isomorphic to the cyclic group Zn. Here's one that you'll do on your homework. If you take the rational numbers under multiplication and you get rid of 0, that's what Q star is, it's the rational numbers without 0 under multiplication, and then you quotient out by the subgroup generated by -1. So under multiplication, this subgroup is just 1 and -1. It's a group of size 2. But if you do that, I claim that you get something that's isomorphic to the rational numbers under addition. So that's probably not so obvious right away, but I encourage you to work it out on your homework, and I think I have an extra hint on that particular homework problem. Now this, you shouldn't be looking at and saying, oh, that's clear, but this is actually known as the second isomorphism theorem. And frequently, many books call the fundamental homomorphism theorem the first isomorphism theorem. And as we'll see, there are actually 4 standard isomorphism theorems, with this one being the second one, and we will return to this topic in 2 more lectures. And finally, here's a result which also should not be clear at all just from looking at it. This will be on the homework, proving it will be on the homework. This says that if you have a group G generated by A and B, and all this means is that everything in G can be written as a product of something in A and something in B, then G mod the intersection is isomorphic to the direct product of G mod A and G mod B. So when you play around with this on the homework and do some examples, hopefully you'll get some intuition as to why this makes a lot of sense. I don't expect you to see it now, but I will say that the proof of this is just by this technique number 2. And let's actually outline that now. Let's start it now, even though we don't have any great intuition as to why this should be true. So let's define a mapping phi from G, remember, not from this group, but from G to that group. So G to G mod A cross G mod B. And there aren't many choices that are natural of how to define such a map. So let's see. Phi of G, we have to send that to, what is this? This is an ordered pair of cosets of A and of B. So an element in this group consists of an ordered pair of a coset of A and a coset of B. So given an element G, what's a natural thing to send this to? Well, how about GA comma GB? That works, or it works as a function from here to here. Now you have to show this is a homomorphism. You have to show that it's onto. That's non-trivial, and it definitely uses the fact that G is generated by A and B. And then the last thing to do is to show that the kernel is equal to N, this group here. So that one I claim we can reason right through. So why is the kernel of this mapping equal to A intersect B? Okay, so what's the identity element in this group? So the identity element is the identity coset in here with the identity coset in here. So the identity element is just the coset A, B, right? The identity coset of each. So when is this equal to A, B? Well, that's if and only if G is in A and G is in B. So this is true if and only if G is in A and B, which means it's in their intersection. So here it's actually very straightforward to show that the kernel of this mapping is indeed A intersect B, which is exactly what we want to be in place to use this technique to prove that this is indeed an isomorphism and apply the fundamental homomorphism theorem. As promised in the previous slide, we will end this lecture by looking at cyclic groups as quotients. This is an application of the fundamental homomorphism theorem. We'll do this by example. Consider the following normal subgroup of Z. Now it's normal because Z is an abelian group, so every subgroup is normal. Here are two different ways to write it. We can write it as 12Z, or we can write it as the subgroup generated by 12. Either way, it's a set of integers that are multiples of 12, and that's the normal subgroup of Z. Now, the elements of the quotient group are the cosets. And be careful, this is an additive group, so the cosets are written additively. The identity coset is just the subgroup 12, which is 0 plus 12. And then the other cosets look like this. So by this we mean 1 plus the group generated by 12 means 1 plus a multiple of 12. So this is the coset consisting of everything that is equal to 1 modulo 12. This is the coset of all the integers that are 2 mod 12, and so forth. Number theorists call these sets congruence classes modulo 12. We say that two numbers are congruent mod 12 if they're in the same coset. Recall how we add cosets in the quotient group, and I say add because this is an additive, not multiplicative group. So to add these two cosets, A plus, I'm going to call this H, A plus H plus B plus H is just A plus B plus H. So in plain English, that means the coset containing A plus the coset containing B is the coset containing A plus B. It should be clear that Z mod, the subgroup generated by 12, is isomorphic to Z12. In other words, this collection of 12 cosets forms the cyclic group Z12. Formally, this is just the fundamental homomorphism theorem applied to the following homomorphism. So there's a very natural homomorphism from the integers Z to Z12 that takes any integer k and reduces it modulo 12. clearly, the kernel of this homomorphism, the things that get mapped to 0, is this subgroup generated by 12. That should be clear, right? Everything else gets sent to something non-zero. These get sent to the 0 element in Z12. So, by the fundamental homomorphism theorem, Z mod the kernel, which is Z mod the subgroup generated by 12, is isomorphic to the image. And now what's the image? This map is clearly onto. Everything gets hit. And so the image is Z12. So, in other words, Z mod the multiples of 12 is isomorphic to the cyclic group Z12. Here is a picture of the isomorphism that we just constructed. And this comes from the Visual Group Theory website. This is one of 1 or 2 images that I used from the website in my whole class. You'll notice that the arrow types here are different than the style that I use. Everything else I make myself. So here we have a homomorphism from the integers z to the cyclic group. Now they call it C12. They don't differentiate between C12 and Z12 being multiplicative or additive. So I'm going to actually cross this out and I'm going to write this as Z12. And this homomorphism just takes an integer and reduces it modulo 12. Now by the fundamental homomorphism theorem, we can decompose this into 2 steps. We can first do Z mod the kernel. So clearly the kernel is this. There we go. So this is the kernel of phi. And I should say that I call this isomorphism I. Here we're calling it phi. So here's the kernel. Here are the left cosets. So if you collapse out by the left cosets, what you get is you get a diagram that looks just like this, but the nodes are labeled with the cosets instead of the numbers. So this map here, this I is different than this I. This relabeling map is an isomorphism that shows that Z12 mod the kernel of phi is isomorphic to the image, which is just Z12. So this is the fundamental homomorphism theorem applied to quotients of the integers and cyclic groups.